Yes. This is how I spend my time on airplanes, making stupid PowerPoint animations. Okay, first a bit about myself. I worked with open source since 1996. I started working as a sort of programmer on the side while studying. Later, I became a sysadmin. I like the bigger building blocks that sysadmin have available. Like as a programmer, I could toil with a problem for 3 weeks. As a sysadmin, I would just install some package and it would do what I've spent 3 weeks doing. I found that much more satisfying. And I started a couple of companies. And in my spare time, I do sour beer. So that's kind of a slow thing to do. Usually takes a couple of years from start to finish, but it's fun. Okay, so start off with a short history of computing. This is from the 60s. This were punch card, batch-oriented systems. They were quite efficient. Like you would load your program from a bunch of punch cards, and you would have the whole computer to yourself. There was nothing else running on the computer. So there was no operating system overhead. However, the user experience was horrible. You would submit your stack of cards, and there would be like a missing semicolon on line 5 of your Fortran code, and you wouldn't actually figure it out until the next day. Yeah. So at a later, in the 70s, we started getting time-sharing systems. So that's the PDP-11, where Multics was written, which later turned into Unix. We started getting multi-user and multi-process systems, which came at a cost. There was sort of, I think, like at the time, I think the overhead was close to 20%, depending on the workload. However, these were expensive machines, so you couldn't really just have one for yourself, so you had to actually share them. But anyone who sort of ever tried to take a hardware resource and use software to split it up knows that there's a cost in doing so. So this is sort of what's led us to sort of how I think like almost every single operating system is designed. You have your user space and you have your operating system kernel. In the kernel, we talk to hardware and we police users because we're running in a higher privilege level. On Intel, this is ring 0, this is ring 3. And between them, there's this supposedly secure barrier, which we used to trust last year, which also kills performance. So my previous job was working in a company called Varnish Software, which made the open source thing called Varnish Cache. And basically what we couldn't do in Varnish Cache was talk to the operating system while something was happening, because you can't talk to the operating system unless you absolutely have to, because the operating system is slow. Because it's a full context switch when you go in and out of the kernel. But interestingly enough, the computing systems of today, they're not multi-user systems anymore. If you sort of survey your VMs in Amazon, how many of them have more than one user? Like, I'm guessing like 99%, they have one user. It's typically called www data or something, or nobody, and it runs your single application. And quite a few of them also only run one process, or you might have like a few processes because, yeah, or one process with threads or whatever. Neither is this one. This is a Raspberry Pi, or yeah, just an example of a CPU-based embedded system. It's also not typically not having multiple users and multiple processes, but we do still use the operating system that supports that architecture. So what's Include OS? What we've done is we've written an operating system as a library. So that has a lot of different sort of components. We have some networking drivers, we have an IP stack, we have some firewall code, memory management. So when we build an application with Include OS, what we do is we actually sort of inject those library functions into the application itself. Oh, and then we slap a bootloader on top of it. And then it's done. There was a missing step in the animation there. So it sort of looks like this. The sort of disk layout it doesn't look exactly like this, but you have a bootloader at the front. You have some libraries. It's all mapped in a single address space and a single application, and it's perfectly portable. I could take an application, write it on my Mac. I could give it to you. You could run it in VirtualBox or send it to Google Compute or do whatever, because the only thing it actually requires is x86 64 instruction set, and one of the networking drivers needs to match. This compared to sort of the traditional approach, where you have your operating system kernel, which has a bunch of standard libraries and a bunch of application libraries, and as this application loads, this system gets set up. So why do we do this? What sort of problems do we actually solve? Well, we can actually make reproducible builds of an entire OS application. So hello to Chris. Is here? No. We also eliminate context switches. So there's no context switches because everything is running in the same context. Like the networking driver and the application are both running in the same context. So basically system calls become function calls. Interestingly enough, there's sort of other approaches to this as well. So for those of you who have there's this open source project called DPDK, which is sort of putting networking drivers into user space. So your application will actually manage the networking card itself using its own built-in IP stack. There's also a similar thing for NVMe storage, where you can actually have your application manage your NVMe storage, which I think is quite cool. And they do all of this because you want to eliminate system calls, because system calls kills performance. Yeah. Small footprint, few updates, so it's cache friendly. Typically, I think like last November there was a problem in the reference Bluetooth implementation, which also meant that all the other implementations were vulnerable, which also means that quite a bit of Linux was vulnerable. And of course, there were shipped updates to this, and quite a few people needed to install those updates, even on Amazon, where I don't believe a single Amazon server has Bluetooth connected. But still, it comes as part of an application, so it's sort of a part of the operating system, because when you ship an operating system, most of the time you can't really expect it to be recompiled in place. You need to support everything that the user potentially can throw at it. And that means that the thing you have to update is huge. It's also really, really hard to reconfigure. So that sounds like a bad thing. I don't believe it is a bad thing. Like, again, a Unix system is shipped, it's meant to be reconfigured. That's what it does. And this has, because at the time when it was designed in the 70s, these machines were huge and big. If you go back to today, what we have today is mostly virtual servers, which are super tiny, and you build them and you can throw them away. And this sort of way of thinking about operating system and applications basically takes that to the furthest extent possible. You can interrupt me if you have any questions or comments. Okay, so first demo, we'll try to write an operating system using this Include OS as a toolkit. So we'll write Hello World as a fast and portable Hello World implementation. Let's see. Everyone can see that? Yeah, good. So this is my favorite editor. The rest of you probably have a VI or Emacs preferences. Awesome. Let's see.
20 years ago, I suggested copy from.
Okay. Hopefully that'll do. Now I'm going to boot this. So we're a bit cheeky. There was no Unix command name boot or nothing in Linux. So we just grabbed that. Sort of a land grab. Okay, so it's now building the whole thing. And it's done building. And it's now executing Kemu. Okay. The operating system is booting, and this is it. It's just running now in sort of virtual machine. It doesn't actually do anything, so it's idling currently. But this is a complete virtual machine. Yes?
What do you need the certificate privileges for that?
What do you need
The certificate privileges?
That's basically because it reconfigures the networking so I can reach that machine from the host system. That's what the privilege bits are. Yes? Okay. So I think, like, to some extent this is cool because, like, we've at least succeeded in making the simple stuff simple. The hard stuff is kind of always hard, so that's a hard thing to address. But at least we've made it the simple stuff simple. Okay. So next thing, like there's stuff you can do because we're in a single address space that Unix can't do. So one of the things that sort of we figured out is when we were sort of running our application in, let's say, Google Compute. In order for us to update that application, that was quite a pain in the ass to do that, because we had to actually reprovision the VM with a new image every time we were updating. Compare that to Unix, where you just rsync over a binary and execute it. So we worked on a bit on a way to update the application. So we now have a stateful way of updating a running application without downtime. That sounds like magic, and it really isn't, because we're in a single address space. So this is our memory. That's our current application that we're running. Does something. It might be, let's say that it's a web server. It's currently serving web pages. And once it boots up, it connects to what we call our master node, which is just handles a TCP connection, and it can sort of send the instructions down to the operating system. So this master node now decides that we want to upgrade this VM. So it pushes down a new image, which is then stored in memory. And then what we do is we just have callbacks to store our own state. So this, of course, includes the operating system state, but it also has to include the application level state if you want to retain that across the update. But that, I mean, that's like implementing, like, to serialize some data structures. That's a rather common task today. So like most people will know how to do that. And then that state is stored, and we just reboot into the new application, and then we restore the state. And then we discard the old application, and we also discard, of course, the state. And on bare metal, this takes less than 10 milliseconds. I think we're down to like 7 or 8 milliseconds. On virtual hardware, it takes a bit longer because, like, you do stuff like we currently still probe the PCI bus whenever we reboot, and probing a virtual PCI bus is quite slow because it's emulated. Okay, so I'll try to show you this as well. Yes?
If you're already using a cloud provider for doing that,
Yeah.
wouldn't it make more sense to simply spawn up more instances
Sure.
Marrying and tear down the old one?
Yeah. I mean, you can do it either way.
It depends on whether it's stateful or stateless.
Yeah, and it also depends on the type of application. So, for instance, one of the things that we actually have delivered to customers are load balancers or firewalls, and you can't you can't really do this. Yeah. Next application, Banana Shell. It's pretty useless. It uses unsecured telnet. Unsecured, as in there's no even password, anything. Huh? Okay, so let's see if I can find. There's supposed to be a window here. There it is. Okay. So we will start running this here. Yeah, so now it's running. The application is running. We can then connect to it. This is Banana Shell. Yeah, there's not really that much going on. It spits out like some status every 30 seconds. So we just need to do some sort of random change to this application. So what I'm going to do is just change the status, the frequency of this. Yeah. So let's say that we want a status update every 3 seconds. And boot -B. -B stands for not boot. So that just build. That's probably what it stands for. Build, yeah. So now we built a new application, a new version of the application. It's like there's a build folder here, and there's that is actually the binary that we're running. Yeah. But we have a little shell script here. Basically, just uses DD, cats that onto port 666 on this IP address. So this is the naive implementation of live update. So it doesn't use anything, doesn't use TLS or anything at all. But it works nicely for demo purposes. So and it sort of redraws the banana and it tells you that it's updated. But the interesting bit, of course, is that the TCP connection survived. So we're able to retain state and retain a TCP connection, and there's nothing left of the original code. We switched out 100% of the code, and we're able to do that in a way while retaining state. Yes, let's go back. That is cool, right? Okay. So how are these things deployed? So I mean, they're always immutable. Live update to some extent changes that, but it's still managed as because we're sort of hot swapping. So we're sort of mutating it. We do cross compile, so it's not like we can't do native compilation. We don't. GCC doesn't run on Include OS. The whole issue of configuration management is completely different because you can't reconfigure anything. So everything moves to the build stage. Everything. You can debug this. Kemu has support for remote debugging with GDB. So if you Google the term unikernel, there's this inflammatory blog post said that unikernels are unfit for production, and one of his major claims is that you can't debug them, which is not true. Because I mean, there's no way we would be able to implement a TCP/IP stack without being able to debug it. Yes. So where can this be applied? What can we use this thing for? So we started out with network functions. So network functions, virtual network functions. These are, the little like firewalls, load balancers, stuff like that that you need to spread around in your network. So we had this project internally called Piranha, where we started building this. We started building this mostly because it's a very well understood application. Like I can write down like 5 bullet points. What is a load balancer? I can give you the same task. Like I think there'll be like a 80% match. Like if we do the same thing for databases, like it'll be all over the place. But like load balancers, firewalls, reasonably simple. Yeah. So we actually had a sort of commercial partner here, and they had a few requirements. One of them was to keep change to deployment under 10 seconds. And what they primarily wanted was load balancing, then later firewalling, then actually DHCP, because they wanted to be able to have like DHCP instances pop up and go away in a network. Because they would provision a network, like a host of maybe 50 Red Hat servers, virtual servers, boot that network up. First time they boot, they want to be able to reach the configuration management system, and they want the DHCP server to be there. Until date, they've been using Cisco, but then turns out that the DHCP service in Cisco was there by accident, and Cisco had to retract it and remove it from their firmware. Lol. Yes. Yeah. So what does like an Include OS firewall look like? So because we merge configuration and code, we actually do have to build things differently. So the first thing we started to do was basically just looking at NetFilter and implementing something similar. But then it kind of struck us that it's not really that ideal, because like NetFilter is initialized with a shell script. We can't run shell scripts. We have to like store it in JSON, and the whole thing felt wrong. And no matter what we do, we still have to rebuild on every change, because we need to build the image. So we do have to. So why not take advantage of this? So this is what sort of NetFilter looks like. You use the IP tables tools to place inject rules into a list that look more or less like this, and then packets arrive and they get pushed down the chain until they match or there's no more rules, or you hit the default rule or something. So basically, read rule, evaluate action, read rule, evaluate action. That's what you do. So here is what we did. So we created a sort of domain-specific programming language, which we call NaCl, or SALT. What we do is actually take this and we transpile it to C++. And then we feed that to Clang and into the linker. And we have a static firewall. A firewall that basically is unable to you can't reconfigure it. It has its firewall rules hard-coded into it. Yeah, I see some of you seem a bit skeptical. But it's the language itself. I think it's reasonably clear what we're trying to do. Like the addition of if statements brought so much clarity. So we did initially like translate a lot of like. I got all my friends to send me all their firewall scripts, and I translated it. And this looks a lot easy. It's a lot easier to read. Then the Oslo Metropolitan University did a project on comparative performance analysis of Include OS versus IP tables with throughput. So yeah, so you probably can't see those things here, but this is the reason that there's 2 lines is because one is filtering on source address and the other on destination port, and that's actually for IP tables. There's a difference because if you're filtering on destination port, you're filtering on TCP properties, and those are modules in IP tables, and they'll actually execute slower. So these are basically, this is on a virtual system, so there's a lot of noise in the data set, but it's pretty clear what happens as IP tables as you add rules to it. So there's here we force the firewall to run through every rule for every single packet. So at about 1,500 rules, things start really to deteriorate quickly. I'm guessing that at this point we're running out of level 1 cache for the rule set, and that's why it sort of starts to go really downhill from there. Whereas basically we're about 2% slower with 5,000 rules than we are with the 0 rules. Yeah, I need to update. So since we actually did this, we've both done tests with NF tables and eBPF. eBPF is this new thing in the Linux kernel where you have basically a little VM jitting code. That code is all over the Linux kernel, and somebody's actually implemented good parts of the IP stack in eBPF. And there's some stellar performance results from it. I would say it's an insanely complex system because it relies on this combination of jitted code and static code, but it performs really well. By the way, this is still a naive implementation. We still haven't spent 1 day on performance doing this. So all of the performance gains we see here are purely because of architecture. Yeah. Second thing, and this is sort of, we're not doing this, but if you have an opinion on this, this is something we really want to talk to you about. So ever since we started the Include OS project, there have been 2 or 3 guys in our community who's been jumping up and down and say, can you please port to ARM? And we're finally sort of giving into them. The reason is the following. We can do small images. So Include OS compiled, typically it compiles down to 2 or 4 megabytes. Basically it's the size of your C++ binary. Yeah, so minimum, and most IoT devices that run Linux today, they ship with maybe 2 gigabytes of flash and half a gigabyte of memory. Yeah, small images. It's reasonably secure, so we ship images which can't be reconfigured. I mean, Linux is built to be reconfigured. We also, by the way, have real-time characteristics. So the operating system is real-time because there's no scheduling. So like, there's nothing that gets in the way of your application. Yeah, ultra low latency. The nice thing about not having an OS is that you have an OS that can get in the way. So this is basically a special case of the other one. So we're talking to some people doing, I don't know, it's high frequency trading. That's not like the most popular topic. But they're looking into Include OS as basically because it's very close to real-time performance. Or I would say a consistent real-time performance. Yeah. Linux is actually quite fast, but if you, let's say that you have this tight little loop, you run through it maybe 10,000 times, chances are 1 or 2 times something will get in the way, and you'll add like 5 microseconds or something to that single one. So which means that it's unsuitable for running things like cars or nuclear reactors. Function as a service, yeah, I think I'll probably skip that, but there's some cool stuff happening with hypervisors. Nobody actually knows. There's this little thing called UKVM. So one of the things that's kind of odd when you're working with, let's say, Google Compute, is there's so much legacy there. So Google Compute instances, they still boot up in 16-bit mode. They run, I think, then emulated, and then they run through like post and BIOS, and then They have like a PCI bus that is emulated on the host side. There's a floppy controller. There's like all sorts of stuff. There's a lot of problems with that. Like the attack surface is huge. Like a few years ago, there was an attack called Venom, where somebody actually found bugs in the floppy emulation. Even though there wasn't a single virtual server with a floppy device, to use a floppy device, there was still a floppy device present in all the VMs. And you can actually use that to break out of the VM and into the host system. So there's a cooperation between some people from Docker and IBM, which created this little thing called UKVM. Basically, it supports like a networking card. It supports a block device and a serial console, and also I think some timer primitives, so you can get timers. And that's it. And it's like there's no like PCI bus to scan or anything. And that cuts down so that I think like they boot, run, and shut down within 10 milliseconds, which basically means that you could actually boot up by, when you get the first SYN packet, and by the time the TCP is negotiated, you can have an instance running. Yeah, I'll skip this. Future work. So what's missing from Include OS? We need to improve, I think, our bare metal support. We have like one physical networking card that we support. That's a E1000. Well, there's a kind of really cool thing that has happened is like NVMe. So I don't know how much you guys know about it, but it's they finally decided to stop emulating rotating hard drives, and at the same time they also got rid of the interface. So NVMe's storage devices are just slammed into the PCI bus. They need to implement a specific interface, and as long as the operating system has support for that interface, it'll work everywhere. Also, it can be virtualized. So compared to like 5 years ago, if we were to add support for SCSI, we had to maybe implement 20 SCSI controllers. Now there's one. We run on most hypervisors except Hyper-V, where we don't support a networking card that they use. Also, there is this other exotic hypervisor called Bearflank, which is my favorite underrated open source project. One of the things that's really cool that it can do is if you have a server that has Sandy Bridge or newer, you can actually boot up and you can actually split it up into several systems. And you run different operating systems on parts of it. And they don't know about each other. They can't detect each other. They're perfectly isolated. If you take a 2-socket server, you could give one socket to Windows and one socket to Linux, and they would live side by side. One could have one networking card, the other could have a networking card. They could have each have their own hard disk. You just need to basically just set up the system and then boot it up. And we want to be able to support that hypervisor. Yeah. In order to do that, we need UEFI support. That's basically it. Next year, we plan on adding support for ARM64. We're working on IPv6. That's actually not that bad. One of the things that sort of caught me, because like people have been whining a lot about how hard it is to deploy IPv6. But the implementation is actually simpler. So it's simpler for actually us to implement IPv6 than it is for most of you to deploy it. Standard is 35 pages. That's actually quite small. The only complex bit is actually the neighbor link discovery protocol. And we also need to improve our POSIX compliance. So for those of you who don't know, POSIX is an arbitrary collection of header files from 1982. Rather random standard of which basically defines Unix. Yeah, it's sort of it has good there's good things about POSIX. So like for instance, if you look at POSIX and you implement a file system that's POSIX compliant, that's like fine for 99% of what you're gonna do with it. It's actually really good. Networking, in POSIX, there's no way to do asynchronous networking. Networking wasn't really that important in 1982, so I guess that's where it shows its age. What we actually done here is that we ripped out our C library, which was newlib, and then we used something called musl. And musl has actually implemented POSIX. So if we can provide musl with the operating system functionality, they are able to stack POSIX on top of that. Oh, yeah, that's basically it. Yes?
So when it comes to implementing POSIX networking, as you mentioned, POSIX networking is garbage. I agree with you on that completely. Some time ago, I was looking at libuv.
Yeah.
Heard of that?
Yeah.
It's used by Node.js.
Yeah.
And one thing that crossed my mind is, if you're dealing with an embedded system, instead of having all sorts of random, wacky, board-specific libraries, having some kind of bare metal libuv would be interesting.
Yeah.
And that sort of makes me think, like, instead of focusing on POSIX, at least the ugly parts, would it make sense to implement libuv? Because then you could also maybe get like Node.js and all that kind of stuff. Yeah,
but Node.js also relies quite a bit of POSIX. There's quite a bit of POSIX reliance in there, just for like small things. Yeah. Actually, the interesting bit behind POSIX isn't really we're not going after POSIX for POSIX itself, but my goal is that, I don't know, maybe later this year or maybe early next year, you should be able to go into your Node application and write npm include, and it will compile your application into an image with the V8 engine, the Node engine, and spit out a little image that you can send anywhere that runs a Node application natively. Node is kind of interesting for us because, like, we're event-driven. The operating system is event-driven. The reason for that is your hardware is event-driven. Like, there's no blocking hardware. like the hard disk can't just slow stuff down. The hard disk will write at the speed that it does, and it will sort of send events to indicate that it's when it's done. Or the networking card will raise interrupt lines. Yes. And since Node has the same event model, it sort of fits really nicely.
Especially because libuv is also event-driven.
Yes, that's what it is.
Building instead of porting the official libuv, it might actually be a lot easier to simply write something that's libuv. Which is just a tiny wrapper around. Yeah, likely. So we're not that really engaged with the Node community because they have like their own issues. But I think but it's not actually that hard. Just 2 weeks ago, we did mostly for fun. We ported MicroPython, and it took us like 2 hours now to port MicroPython. So that's a limited amount of libraries, but I think and there was no networking support. But other than that, it seems that even just the small amount of POSIX we have will go a long way. Yes.
So your example was in C++. How
Yeah.
much of like standard templates or of these other?
Mostly except for threads. So we had thread support before Christmas, and we ripped it out. We're going to add it back in again. Thread support will be slightly different. It will be because since we don't schedule, threads are kind of weird. So on an 8-core system, you can have 8 threads. If you're happy with that, then sort of that's it. But you can't have arbitrary number of threads. But we have coroutines and fibers as well. So we basically emulate threads quite efficiently. So what we basically do is just run, and every time we see something that looks like a blocking file system call, we just jump back to the event loop. That's the same thing, the same way Go does it, I think.
As in C++ coroutines, as in what Clang supports in the latest version?
C++ 20. It's not done yet, but
Those kinds of coroutines you're talking
yeah, we talked to the guy who owns that part of C++, and we're doing a presentation in August about Go routines in C++20. So we hope to be able to have Include OS as the sort of reference implementation for Go routines for coroutines by then. Yeah, my alma mater, which is the University of Oslo, by the way, where when I was there, I learned to program in Simula, which is a sort of first object-oriented programming language. One thing I didn't know, which is at the time I figured it out just a few months ago, that Simula 67 had coroutines as well, which is kind of fun. Which is coroutines is coming back. Yes. Any other questions? I don't know how we are when we're supposed to end. 9 minutes. Okay, so we have plenty of time for questions. Yes.
So, I'm not way out of code now, so excuse me. That ability to replace the running image
Yeah.
in less than 10 milliseconds.
Yes.
Has that got any? It's presumably got implications that if you're the naive user of the other end, you would have no idea that something changed.
You would have no idea that it's happening?
Yeah.
Yeah? That's the point, yeah?
Yeah, well, it is the point, but the flip side of that is that something you trusted could be trustworthy temporarily for a certain amount of time, then momentarily tweaked
Yeah.
and put back to the trustworthy one. And you would be absolutely none the wiser. Something was changed.
Of course. Yeah.
So, I mean, you always have to trust the sysadmins.
Yeah.
But
I mean, if you have the keys to the castle,
yes.
you can do some weird stuff. But I mean, it's the same thing with you can do the same messy stuff with Linux. Just write random stuff in the syscall tables, or there's like you can compromise a system, Linux system in milliseconds if you know what you're doing.
It'd just be easier to make that harder to detect.
Yes, but you have to have so interesting bit is it's really hard to compromise a unikernel because it's so for instance, when you attack a Unix system, if you know the architecture that you're attacking, you have the system calls are numeric. So like I don't know, I think like on my Mac, the system call number 4 is write. System call number 1 is open, and 2 is close, I think, or something. So basically, I can write perfectly portable code that will run on any Mac OS or Darwin system that opens a certain file, writes some stuff to it, and closes it, and that the binary code for that attack can be then shipped in and through a buffer overrun, just injected. And in a unikernel, you might have a write call as well, because maybe you have a disk but you have no idea where that is, where it's based, because it's a 64-bit address space, which is randomized every time you rebuild it. So it's kind of quite hard to find. In addition, you wouldn't really know what to do with it, because like even if you're writing stuff to disk, that doesn't really change anything, because the operating system is not on disk, it only resides in memory. So yeah.
This is nothing really to do with Include OS, but have you experimented with safe stack? Like where what could also be a very good way of securing this is to Clang has this compiler option where it assumes that you have 2 stacks instead of 1. One that can hold all of the buffers that can overflow, and ones for which it has proven that they can't overflow. So function return addresses, some integers in the stack, they all go in one place, and all string buffers, they go in the second stack. And the only thing you need is like some fat local storage to keep track of the second stack pointer, blah 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 blah. But I would assume that something for something like Include OS would also be a really good argument.
Yeah. Yeah.
Yeah, it's just a matter of passing a single compiler flag and making some changes to Include OS website.
Yeah, we actually we link manually, or not manually, but by we write our own linker scripts and stuff. It's more involved than not turning on a compiler flag. But it's I'll look into it. It sounds interesting. Kind of security for some people. Security is one of the most interesting points here. Okay? Yes?
What languages can I code in and implement Include OS?
Yeah, the question, so what languages? So currently it's mostly C++, and so the muscle branch is currently merged into our dev branch. It hasn't reached the master branch yet, and it'll then need to hit a release. So I expect us to hit that release within a month. Once we have that, we have this limited but expanding set of POSIX. And then we will basically be able to start adding language runtimes. The nice thing about writing it in C++ or C is that you can do a lot of stuff. You can accept other runtimes quite easily because they're typically implemented in C and C++. Which one would you like to see? Rust. Okay, yeah. I think like Rust spits out ELF binaries.
Or Rust is very much.
Yeah.
When Rust looks out, I suppose it's in C.
Yeah. So if you can compile static Rust code on Linux, so currently sort of our open SSL support, actually we take the Linux binary, the statically compiled binary, and we use that on Include OS because that code actually doesn't contain any system calls, so it's actually portable code. Yeah, no, but Rust, yeah. Yeah, we need to replace the system. Yeah, we need to look at how it interacts with the operating system.
If you're going to look into Rust, something that's worth keeping an eye on is where Rust made a mistake initially is to have something called lit standard.
Yeah.
This is completely bloated library containing file system abstraction and network abstraction. And 99% of all the existing libraries, they all depend on lit standard. So
okay.
If you don't have lit standard, well, you're screwed.
Okay.
But now the Rust project is sort of coming back on that, and they also realize that that's a bad decision for a systems programming language. So in the long run, lit standard will sort of go away, and there will be like a lit net, a lit FS.
I think Rust will have its own unikernel soon. That's the final question. Yes.
Does the system run virtual memory or physical memory?
Virtual memory. Yeah. So we just implemented paging around Christmas. Okay. So thank you very much for listening.